Hey everybody. So what is WebAssembly? Why does it matter? And more importantly, why should me, a web developer, care about WebAssembly? So if you read web development blogs or just follow people on Twitter, you know WebAssembly is a pretty hot topic, especially over the past few years. But if you Google it, most of the blog posts you'll find are sort of like this one here, talking about how WebAssembly will allow you to create web apps using languages other than JavaScript, about how people can port over their gaming engines and all these really cool things and run them in the browser, which sounds cool. It sounds awesome. But for me, somebody who's a JavaScript developer, I kind of started thinking, well, is WebAssembly even important to me? Is it only important to people who, code in other languages? And the answer is it can be, but you sort of have to understand how the web works and how stuff is ultimately compiled to run from the browser and onto your system. So to understand that, I'm not going to go over it in great detail, but I will recommend reading this blog post by Lynn Clark. She works on the Firefox team, does a ton of stuff with WebAssembly, and she sort of explains how we got from the early versions of JavaScript to the versions we have now, and it's using this technology called Just-in-time Compillers. So to really understand that, you kind of have to understand how JavaScript is really inefficient. So let's say, for example, we have a function called add together, right? And it takes two things, it takes A and B, and it just returns A plus B. So for us, we can look at that and like, oh, it's something that gives us back a sum of two numbers. The problem is JavaScript is not a strongly typed language, so A and B can actually equal anything. A could be a string, B could be a number, A could be an array, and B could be a string, etc. So because of that, the result here is very different. So why is that important? So think of programs like the browser. They ultimately have to run on assembly languages, which is the language your processor understands. So that's going to be strongly typed. So when just-in-time compilers were introduced, what they would do is they would create a compiled version of this function, the instance in which it is run. So let's say the first time we call add together, we're like add together 1, 2. The just-in-time compiler might say, oh, this is a function that accepts two numbers. I'm going to create a compiled version of that checks to make sure the two numbers, and if so, I'm going to run the compiled version that I have. So if we kept running this, it actually becomes more and more efficient because it says, I can safely assume at this point it's going to be two numbers. But then we run it like a fourth time or whatever, and we pass it something like this, or even undefined, right? That could happen. And then it tries to run that compiled version. It completely breaks because on the assembly level, it's not receiving two numbers. It does this process called bailing out, where it essentially starts this whole process over again. And that's when JavaScript becomes really inefficient. So just-in-time compilers made it way more efficient than pre-compiling it or running it at runtime. But it's still not as efficient as a strongly typed language. It's still not as efficient as writing something in let's say Rust or C. So this is sort of where WebAssembly comes in. WebAssembly allows us to write pre-compiled versions of our functions to forego this whole just-in-time compiling, bailing out loop. If we say, I know for a fact that my function is always going to accept numbers, I'm going to write my own compiled version in WebAssembly, or compile it to WebAssembly and run that in the browser. And then JavaScript doesn't have to do this crazy sort of loop of trying to figure out the types of these functions and recompiling, bailing out, etc. To demonstrate that, I spun up a pretty simple example here. It's just a dumb JavaScript app. Let me run it right here. npm start. And I built this using this Hello WASM pack. I'll link to that into the description, but it's a way you can very easily spin up a WebAssembly project with Rust. You don't need to use this, but it just gives you some nice boilerplate here. So let's actually just go to our little app here. It is literally just an app that adds numbers together. So let's say I want to find the sum of all digits between 1 and 100. That's what this app does. And I click sum it up, and it shows me, okay, the sum of this is 5050, and this took 0 seconds to run. So if we look at the code, I did purposely write this in a really, really inefficient way to sort of demonstrate the point. And I didn't have a complex algorithm on hand, so I wrote one that is just really inefficient because there is a much easier way to sort of get around this without summing up every single digit. But just to prove the point, we start with the number 1. We start with the starting value, which is the number that we input into our little input over there, and then we just keep adding 1, and we return the sum, and then we judge how long that takes. So the sum of the digits between 1 and 100, 5050. What about the sum of the digits between 1 and 1000? Well, 500,500. So you'll notice a pattern here. If I keep adding zeros, we sort of just add 1 0 here and add 1 0 there. So what happens if I go to a really high number? Let's say 1 million, right? So 1, 2, 3. What is that, 1 million? Yeah. And I click add. Okay, so we got even bigger. It's starting to take a little bit longer here. So what happens though if I go to a really big number? Let's say 1 billion. I want to add digits between 1 and 1 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? That should be 1 billion. We're going to sum it up. And it took a little longer there. See, it took 1.79 seconds. But the weird thing is we got a different pattern here for our number. We didn't get the just add a number of zeros between these two 5s. And the reason for that is JavaScript actually has issues with numbers that are past a certain point. I forget what exactly the number is, but it essentially can't deal with really big integers, and it can't run arithmetic on it. It's not going to give us an error. It's just going to give us back bad data when the numbers get that high. So to get around that, we can leverage a different data type. So right now we are just parsing this as an int, but if we parse this as a big int, we can run calculations on these numbers. So we have to keep all of these as big ints, unfortunately, to run our arithmetic here. And again, maybe there's a more efficient way for us to run this that sort of says, all right, if it's above a certain amount, parse as big int. But again, just to sort of prove the point of how JavaScript isn't quite as efficient. So let's make sure this still works. I sum it up with 1 through 1000. It's telling me big ing is not a thing, and it isn't. So let's refresh this and sum it up there. So we're still getting all these digits, or we're still getting the correct answer here. It's starting to take a little bit longer because big int does take up more memory than a normal parse int. But let's go with that really big number. We're going to do 1 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. So add up all the digits between 1 and 1 billion. And we're going to click sum it up. And we're going to wait here. We're going to wait here for quite a while. Okay, so it finally stopped running, and you can see it took quite a while. It took almost 2 minutes. Part of that is that my system's resources are being sacked by Streamlabs here, so it probably would have been a little faster if I wasn't trying to screen record at the same time. But regardless, we shouldn't expect our web page to take up that many resources, and certainly wouldn't expect it to take this long. And the reason, again, is because JavaScript just really isn't that efficient. One, at adding big numbers together, and two, it's not efficient at creating compiled versions of this function. So this is when we get into writing in a more efficient version in a lower level language like Rust. So as I said, I used this npm package called WebAssembly pack. It creates this boilerplate for me. So it puts the actual web app in the www directory, and then my Rust file is in the source directory. So I created this function already. I pre-wrote it. in Rust. And just to be clear, it is just as inefficient as the JavaScript version. It's still going to start with number 1 and then add number 2, add number 3, etc., all the way up to whatever number it's given. So this is a strictly typed language. We have to define what type our variable is here, U64. So this is an integer that goes above a certain amount. So normal integers only go up, cover negative numbers and only go up to a certain amount in Rust. This, we're saying I don't have negative numbers and I want to include really, really high digits. So it is essentially the same as big int in JavaScript. So yeah, we just say we're going to start at 0 and we're going to keep adding. And then eventually we're going to return until we've gotten to whatever number this is. So how do we actually run this in JavaScript? Well, this package will walk you through it. You can actually just run wasm pack build. So if we run wasm pack build, it will create a compiled version into this pkg directory. You can specify how this gets built out, but then in our web app, we can load that npm package here. So we're going to say we're going to have some dependencies. This was just a test file I was doing. This is the one that we're looking at. I named it you win some, you lose some, and we're just going to point it to a file, which is here. If you actually look at this, it generates its own package, JSON. You can look at this. Again, this is auto-generated. I didn't write this code. You can try to look at the WebAssembly file, but it's going to look like gibberish in VS Code. So we're going to then import everything from that package. So think of it as its own npm package. So import everything as, we'll call it something clever, from you win some, you lose some. So something clever is going to be an object that has keys that align with the functions that we have here. We only have one key here, so we just call it add numbers. So let's comment you out. So we're no longer going to do that, and we're going to call let sum equals something clever dot add numbers. So you can see it already came with the types. So VS Code knew what to give it, and we're going to give it starting value. So we're still going to use big int here from JavaScript, and we're going to pass that type here, and it should be, again, the same result. It is still adding numbers inefficiently, but now we're going to see the difference between adding big ints with Rust and adding big ints with JavaScript. So let's come back to our web app here. We'll just refresh it, make sure everything's loaded. So again, before it took over 2 minutes to run, adding them up for a billion. Let's just make sure it works with even a simple number. It does. So we go 1, 2, 3, 1, 2, 3, 1, 2, 3, and we click sum it up. Just as inefficient as last time, adding all the numbers between 1 and a billion. But you can see now it only took 5 seconds. And again, that's with my system using resources to run Streamlabs and some other apps. It should be more efficient if I'm not using up so much, but you can see way, way faster than, 2 minutes and change. So I hope this sort of demonstrates the basic concept we have here of, if I'm going to do something, I'm going to write a function that I know is always running with numbers, always running with strings, etc. I can pre-write that function in something like Rust and use WebAssembly to create a low-level version, a pre-compiled version of that function, and I can save JavaScript the hassle of the just-in-time compiling and bailing out loop that makes JavaScript really inefficient because it's a loosely typed language. So this was sort of a toy project example, but I hope it sort of just demonstrates the efficiency gains that even though you are just a JavaScript developer, you can still get the gains of WebAssembly without having to, just port over some huge engine written in another language just to run it in the browser. Anyway, that's it. If you have any questions, leave them below. My email is in my bio. Feel free to shoot me an email if you have any questions on that. I'm also going to link to these great blog posts by Lynn Clark, so be sure to check it out. they can explain just-in-time compiling and how stuff runs in the browser so much more efficiently than I can. Yeah, she is a great resource if you're interested in WebAssembly. Thanks.